we have proved that every convergent sequence is bounded. So boundedness is a necessary condition for convergence. This means that sequences that are unbounded cannot converge. So this is a necessary condition for convergence. And mathematicians, whenever they have some necessary condition, they always want to ask, is this condition is also sufficient? Because there could be no convergence without boundedness, but would boundedness alone be enough for convergence? So think about this for a moment. So is the converse true? That's what I was trying to say. Does every bounded sequence converge? And we know that the answer is no. So for example, for the sequence an minus 1 to the power of n, it is of course a bounded sequence. The absolute value of every element is no bigger than 1, but we have proved that the sequence is not convergent. And so, okay, we will ponder about this and consider what is the reason that this sequence does not converge. And we may also note that the sequence kind of consists of two natural sequences. In a way, we can split it to convergent sequences. Now, this is not rigorous, but it's just for the intuition. So we could think of splitting it to the sequence which is constantly 1 and constantly minus 1, and those constant sequences are obviously convergent, but to define what it means to split, we'll need the notion of subsequence. So, and we can ask another question: what other condition may we impose, right, or minimal condition? What else do we need to make a bounded sequence converge? And so if we consider the sequence of n, which is minus 1 to the power of n, we may come to the conclusion that the reason that the sequence failed to converge because it was oscillating from minus 1 to 1, and therefore in every interval around 1 and around minus 1 we had infinitely many elements of the sequence, which cannot be. I mean, if we have a limit, then every epsilon ball has to contain all the elements of the sequence except maybe for finitely many. So it's this oscillation of the sequence between those two values, it's oscillating infinitely often, that the sequence failed to converge. So yeah, so how can we prevent from a sequence from being oscillating, or what is the opposite of being oscillating? And the opposite, in some sense, which comes to mind, is that the sequence is monotone. So monotonicity is the opposite of oscillation, right? Because it has to be only always increasing or always decreasing, in a sense, right? So if we have a sequence that is monotone, it cannot oscillate wildly, right? It has to only grow or only decrease. And so the natural question to ask, let us first now make this definition. So what does it mean for a sequence to be monotone? So a sequence, if monotone, I had to add here monotone increasing, if for every n, an is no bigger than an plus 1, and the sequence would be monotone decreasing if it was the opposite. If an were to be greater than an plus 1, and then the elements would be decreasing. Here, this is the definition of a monotone increasing sequence. And note that this less or equal that we have here, this means that this is just monotone. If you want the sequence to be strictly increasing or strictly decreasing, then we would say that it is strictly monotone or strictly monotonically increasing or strictly monotonically decreasing, and then the inequalities here are sharp. So an is strictly smaller than n plus 1 for a monotonically strictly monotonically increasing sequence, or an is strictly bigger than n plus 1 for a monotonically decreasing sequence, right? And so if we were to look at this monotone sequence, and which is bounded from above, we see that this sequence kind of forced to converge, right? So it will be, I mean, we'll need to prove this, but observing the following figure, we see something that becomes intuitively clear. Suppose that we have the sequence that has to increase, but it cannot increase beyond some value. So it's increasing and it has to stop somewhere, right? So it's kind of forced to converge. And that's a good intuition, except that we need to be careful. And proving this is not so obvious. We'll see why. Okay, So, for example, it's not true if we were considering a sequence that is of rational numbers that is strictly contained in the rational numbers, and we're considering it as a sequence of rational numbers. So consider the following example. So consider the sequence of rationals. It's q1 would be 1, and q2 would be 1.4, and then qn would be the first n digits of the decimal representation of the number, the square root of 2. It's a real number, but it's not a rational number. So this sequence would be monotonically increasing sequence of rational numbers. The numbers are rational because we stop after each sequence element contains is a finite expansion, right? So every such number who has finite decimal expansion has to be rational. It's just, right, this number divided by 10 to the power of n, right? It's just we write the digits and then divide it by 10 to the power of n, and that's our fraction. So obviously it's rational. So this sequence is monotone increasing sequence, and it is also bounded, and it is bounded by this number square root of 2, but that's a real number which is not rational. So this sequence, if we were to consider it as a sequence in Q, this sequence does not converge in the rational numbers, as it is limit. The limit of the sequence is not a rational number. So, and this is a very important point, because to prove this for the real numbers, this means that we'll have to use some crucial essential property of real numbers that distinguishes it from the rational numbers, right? And so let us prove indeed that this sequence of real numbers converges in the real numbers. So if we consider qn minus the square root of 2, then it's not bigger than, so the first n digits are the same, and so the difference is no more than the 10 to the power of minus n. Now here, if we would want to find this epsilon and prove according to definition, we could have this, if we want this to be smaller than epsilon, then we would have this playing game with logarithms. I don't want to involve this. So what we'll do instead is just observe, it can be easily proved, that 10 to the power of minus n is smaller than 1 over n. It's just an exercise to prove. You can prove it by induction, but it's also intuitively clear that the power here grows much faster. But either way, it's easy to get convinced that this is the case. So we'll just use that this distance of qn from the square root of 2 is no bigger than 1 over n, so that that inequality that we'll be solving will be easier, and we will not be finding the minimal n of epsilon for each it holds, but sum n of epsilon. So now if we want to solve this inequality that this is smaller than epsilon, we've already seen that if we choose n of epsilon to be that, then for every n that is greater than this n of epsilon, we would have this, and so indeed the sequence converges to the square root of 2. The sequence of real numbers is indeed convergent. But it is not convergent in Q. Its limit is not in Q, but it is convergent in R. Okay, so the limit of the sequence is indeed the square root of 2. Okay, and so to prove the following theorem, we'll need to use an essential, as I mentioned, essential property of the real numbers that distinguishes it from the rational, and it's about the constructions of real numbers which makes it special. And it's exactly that those kind of limits, that like the square root of 2, are real numbers, and it's the completeness. So now let us recall the completeness axiom that says that we'll be proving the following theorem. But so every monotone increasing and bounded sequence that is bounded above. So let's restate this. Every monotonically increasing sequence of real numbers that is bounded above is a convergent sequence. Okay, so to prove this, what is the property we're looking for? And as I said, we're looking for completeness. So let us now recall the axiom of completeness, which says that every bounded subset of the real numbers has a supremum, which is the least upper bound. This is the axiom of completeness, which distinguishes the reals from the rational. Now, that's one approach when we construct the real numbers from the rational numbers, is to say that, okay, we add the axiom of completeness, and that's the way to construct real numbers. There's other ways with Dedekind cuts, and there are ways with equivalence classes of Cauchy sequences. We'll cover it later. But for now, let us take this easy step that we add this axiom of completeness. So this axiom of completeness is what makes the real numbers into a complete metric space. But let's see what it means. So the axiom of completeness for when we're going to prove this theorem gives us a candidate for a limit, because here when we said every monotone increasing and bounded above sequence of real numbers is a convergent sequence, like how would we find a limit? And now when we look at this axiom of completeness, we say, well, okay, if every monotone increasing sequence, we can see it as and bounded, we can consider the set of all the sequence elements, which is a bounded set, right? And it is a bounded set, and therefore it has a supermum, least upper bound. And the supermum is this candidate to the limit, which will prove that it is the limit. So the axiom of completeness gives us a candidate, and so we're going to prove that a bounded sequence of real numbers, which is monotonically increasing, is converges to its supermum. Okay, and so why would this approach fail in the rational numbers, right? Well, because exactly Q is not complete. And what does it mean? So if we consider this set, for example, right, of rational numbers, all rational numbers such that Q squared is smaller than 2, then this set is bounded. It's a bounded set of rational numbers. And the supermum, what would be the upper bound? The upper bound would be 2, but the least upper bound would be the square root of 2, which is, of course, not a rational number. So this set has no supremum in Q. That's the reason the Q is not complete, and it will fail for Q, but we will succeed in doing this for R. Okay. So let us prove. So let AN be a bounded monotone increasing sequence of real numbers. Well, then, if we were to consider this set, right, then this is a bounded set of real numbers. Now we invoke the axiom of completeness and say, okay, if this set is a bounded set of real numbers, it has a supremum, right? And so let M be the supremum of this set, that's the least upper bound. So it's an upper bound, which means that every element of the sequence is smaller or equal to M, right? So this is just saying that M is an upper bound. And saying that M is the least upper bound is to say that if we ever so slightly decrease M, it will fail of being an upper bound, because M is the smallest possible upper bound. So if you ever so slightly decrease M, it will not be an upper bound. Okay. So by definition of the supermum, this means that for every positive epsilon, M minus epsilon, which is slightly smaller than M, is not an upper bound for the set. Well, what does this mean? Well, it means exactly that there will be an element, there will be some index, call it n of epsilon, might be dependent on epsilon, such that M minus epsilon would be smaller than a n minus epsilon. Why? Because M minus epsilon is not an upper bound for the set. So there will be an index, which we call it by the name n of epsilon, right? And it's an element of the sequence that will be bigger than this number, which is not an upper bound. But M is an upper bound, so a n of epsilon still cannot be bigger than its upper bound, so it's smaller or equal than M, and clearly it is smaller than M plus epsilon. If we slightly increase the upper bound, then of course it's going to be bigger than that. But and it looks like we've succeeded, right? It means that a n of epsilon minus M is smaller in the absolute value, smaller than epsilon, but not quite. I mean, it works for every sequence so far, right? For every sequence of real numbers. And we didn't use monotonicity so far. What we actually need to prove is that every index that is greater than n of epsilon would also have this inequality. And this is where monotonicity comes into play. So since now this sequence, by assumption, is monotone increasing, this means that for every n that is greater than n of epsilon, then a n of epsilon is going to be smaller or equal than a n, right? Because the next element is going to be bigger, and every element here with bigger index is going to be bigger than that. So now what we have is that for every epsilon, we have shown there exists n of epsilon. such that for every n that is greater than n of epsilon holds the following. So first of all, of course, m minus epsilon is going to be smaller than n of epsilon. Since the sequence is also monotone, then an is bigger than that, so we're going to have this. But since m is an upper bound, I mean that's a supermum, that's least upper bound, this means that an is smaller or equal to m. And in particular, it's smaller than n of epsilon. So therefore, we have proven that for every epsilon there exists n of epsilon, such that for every n that is greater than n of epsilon, an is between m plus epsilon and m minus epsilon, which means that an minus n in the absolute value is smaller than epsilon, which means that an exactly converges to m, right? So just restating, so we have showed that for every epsilon we can find a natural number n of epsilon, such that for every n greater than n of epsilon, an minus m will be smaller than epsilon, which means that the sequence is convergent and the limit of the sequence is m, and m is the supermum. So we have proved that. So every monotone, increasing, and bounded sequence of real numbers is convergent to its supermum. Now, we could have another theorem that says that every monotone, decreasing, and bounded below sequence of real numbers is also a convergent sequence. And, well, how would we prove it? Well, the proof is, well, I hated when I was a student somebody would do it, but the proof is an exercise. But in this case, it's really important that you do this exercise to verify that you understand all the stages. So, in fact, the axiom of completeness is equivalent, saying that every set that is bounded above has a supermum. It's equivalent to saying that every set that is bounded below has an infimum. That is the greatest lower bound. That is, if you ever so slightly increase it, it will fail to be a lower bound, and there will be a number smaller than the lower bound. So you need to do exactly the same, follow exactly the same steps, but for the infimum instead of supermum, right? So if you have a sequence that is monotonically decreasing and bounded from below, then it has an infimum. And then for this infimum, you do exactly the same steps. So, yeah. Maybe I'll add some comments about this, but it's a really good exercise for you to do. Okay,